Hello there. In this lesson, we're going to learn about simplifying assumptions that we can use to speed up the process of solving equilibrium constant problems. The one that we're going to look at, the first one, is going to be the perfect square. So those are when the constant has a square on the top and the bottom. And the second one is when there is a large or small constant, we can use some assumptions to shorten the problem solving there and avoid having to use things like the quadratic equation, which is a little slower. So we're hoping to take a little more direct route here using some simplifying assumptions. Alrighty, so the first one we're going to look at is the perfect square solution. So if you have a reaction where you are working out some unknowns for reactions of this type, you might have something like 0.1 mole per liter minus x here, and maybe the same thing here. And then over here it might be 0.1 plus x and 0.1 plus x. So when you put this into your constant, you're going to end up with 0.1 plus x squared all over 0.1 minus x squared. So if you see you have squares on the top and the bottom, you can use a perfect square solution. Likewise over here, we have a constant, and let's say you have like 0.1 minus x on this side, and this was maybe 0.2 plus x and 0.2 plus x. They do have to be the same or else it won't really work. So for this constant, you'd end up with 0.2 plus x squared on the top and 0.1 minus x squared on the bottom. So if you have a setup like this where the top and the bottom both have squared values, well then you can simplify by taking the root of both sides, and that gets rid of all the squares, and you don't have to do the quadratic equation, and you don't have to deal with any exponential values. Alrighty, so let's solve this perfect square. We are starting with a concentration of 0.5 moles per liter of the hydrogen, 0.5 moles per liter of the iodine, and no hydrogen iodide. So this reaction has to go to the right. It means you're going to lose some here, you're going to lose some here, and you're going to gain 2x here. And that means that at equilibrium, it's going to be 0.5 minus x, 0.5 minus x, and 2x. So if we put this into the constant expression, the constant is going to be equal to the hydrogen iodide squared all over the hydrogen times the iodine. So the constant is 64, and on the top we're going to have 2x squared, and on the bottom we're going to have 0.5 minus x squared. And so the trick then is to take the root of both sides, and we'll go up here, and that makes it an 8. And on the top we've got 2x, and on the bottom we've got 0.5 minus x. So this is a lot easier to solve. So then it's 8 times the 0.5 minus x equals 2x. So that is 4 minus 8x equals 2x. So that is 4 equals 10x. And we'll go up here again. And so that means we're going to divide both sides by 10. So x equals 0.4. Great. So once you have that, you can stick that back in for the original values. And I guess I should have kept a few more sig figs here. So that'd be a 0, 0, and these are 0, 0s. So I'll do a different color. So 0.5 minus 0.4 is 0.1 moles per liter for this one, and the same for this one. And then 2 times that, so 2 times 0.400 moles per liter would give us 0.800 moles per liter for the other one. Great, so we got concentrations for all of them using the perfect square. All right, so their second simplifying method that we're going to use is when the equilibrium constant is really, really big or really, really small. And once that's the case, you can kind of make the assumption for at least the big values in the equilibrium that the shift will be like almost completely to one side or the other, right? Because a large K means that most of the matter is on the right-hand side, and a small k means most of the matter is on the left-hand side at equilibrium. So if you have things where the concentrations that you start with are very close to the concentrations that you're going to have at equilibrium, then the change is going to be very small, and there will be some parts of it that you can make an assumption that the change will be negligible. So a very, very tiny change. So if you have a large value and you're changing it by a tiny bit, once you round it to the number of sig figs that you have, you end up not really changing that value at all. Now the other possibility is if the starting concentrations are a long way from the equilibrium concentrations, right? If the K is a lot different than what you're starting with. So that means you can have a big shift, and you can use a simplifying assumption that the equilibrium shifted like completely one side or the other. It's not entirely true, but it's close enough again with the sig figs that you can use that assumption to simplify your solution. So how do you tell whether or not you can use this? Well, there's this little trick called the 100 rule or 1,000 rule. I've seen it a couple different ways. Basically what you do is you take the larger value, whether it's the concentration or the constant, and you divide the big one by the smaller one. And if you get a value of 100 or more, or 1,000 or more, then you can probably use all your simplifying assumptions, as I'll demonstrate. All right, so let's go. So looking at our first situation here, we have a value of concentration of 0.550 moles per liter, and we have a very tiny equilibrium constant here. So if I take the concentration, the 0.500, sorry, and divide that by the 8.5 times 10 to the negative 8, we're going to get a huge number. So 0.550 divided by 8.5 times 10 to the negative 8 equals, and I get a number that's like 6.5 million, right? So 500, way over 100, right? Which is way greater than 100. So therefore, simplify. So that's how you can tell that simplification is possible. Now the next thing is like, how are we going to simplify? So you can see that this is a very tiny value of K, and that means that at equilibrium you'll have a large amount here and small amount over here. So that means it's pretty much at equilibrium. Right now you're starting with all of it on the left and nothing on the right. So this has to go to the right, but it's only going to be a small amount, right? Only a teeny little bit is actually going to shift to the right there, and you'll be at equilibrium. So this is a small change, and that means that this minus 2x here will be really tiny, and these plus x's will also, that's a 2x, plus x's will be also very small. So the simplifying assumption we can make here is that if we have a larger value here and we're changing it by a teeny tiny amount, that we can ignore the change to the large value. We can't ignore these because it's being compared to 0, so it's has to be worked out. But this teeny tiny value, if you're subtracting a small number from a much larger number, well then the change to the overall concentration will be negligible if we round it back to our 3 sig figs like we have here. So let's see how that would look. Okay, now we can solve this using our simplifying assumption. What we're going to see is, again, that since at equilibrium this is going to be large and these are going to be small because of the size of this value for K. And we see that we already have the large value on the left and we have nothing on the right. So even though it does have to go to the right to get to equilibrium, we know that it's not going very far. It's going to be a teeny tiny little shift, which means this value for x is going to be very small. And so when we subtract this very small number from the larger value that you're starting with, the difference will be negligible, and we can ignore it and make our solution a lot easier. So what we do is we just ignore the change to the large value because it'll be negligible compared to the amount that we have, and we solve for the rest of them. So that'll look like this. You'll have 8.5 times 10 to the negative 8 for the constant, and on the right side we're going to have 2x squared times x, and for the left side we're just going to go with the 0.55 and leave out the minus 2x, which makes it a whole lot easier to solve. So to follow through, we will multiply the bottom by the other side there, times 10 to the negative 8. We're going to multiply that by the 0.55. Oh, looks like I forgot my square, right? That should be a square. And this, if you multiply this together, it's going to be 4x cubed. And we'll go up here to finish it off. Let's see what that comes out to. 0.55 squared times 8.5 times 10 to the negative 8 equals. So you get 2.57 times 10 to the negative 8 equals 4x cubed. And then we're going to divide both those sides by 4. 4's cancel out. End up with x cubed divided by 4 gives me 6.43 times 10 to the negative 9. And then we're going to take the cube root of both sides, and we'll do this. 1 over 3 equals, and you end up with 1.86 times 10 to the negative 3. So there you go. A very small change, which would be negligible if you plugged it in for that value that you have. And this concentration here could then be used to solve for this concentration, and then you would double it to get this guy. So you'd have all three. The concentration here, I'll put them a different color again. So the concentration here, we are assuming to be no change, so 0.55 moles per liter. The concentration here is 1.86 times 10 to the negative 3. I guess we're going with 2 sig figs. That'd be 1.9. And this would be 2 times that, so times 2 is 3.7 times 10 to the negative 3 for this guy. So there you go, all three concentrations all worked out. Okay, the second situation we're going to look at is when the constant and equilibrium conditions are very different from the initial, right? So with this one, we've got a big value of k. We're going to use the same reaction. So for a big value k, that means at equilibrium, you're expecting lots on the right-hand side and very little on the left. And so that means that this shift here is going to be a very large shift. And so we're not going to have any negligible amounts here. We're going to have big changes, right? So when the k value is this big, that means that something on the left is going to be ridiculously small, get like almost all used up. And so that's the assumption. You can assume for the big values at least that that one of the components being used up goes almost to 0. So since we only have one thing on the left-hand side, this would be like a minus 2x here again. This is going to be plus 2x over here. It's going to be plus x. And so 0.55 minus 2x is going to be approximately equal to 0, right? That's going to go so small that it's going to be pretty much all used up. And so you can use that to work out the changes for the other two. This approximation here, that is your simplifying assumption for this one. Okay, let's solve this by simplifying. We know that this is a big shift to the right because the constant is very large, which means these are going to be your large values and this is going to be your small value, right? And so that means that these guys here are going to be approximately equal to 0, and so that's your simplification that we're going to do. So over here, let's do it. We got 0.55 minus 2x equals 0. And so 0.55 equals 2x, and x equals 0.275. 0.55 divided by 2 equals, 0.275 moles per liter. So we'll leave it like that just for now, and then we can round it off later. So we can use that then to plug in for these two large values, right? So we'll use our assumption for all the large values. And so we know then that the 2x here is going to be 0.55. And for this guy, it's going to end up being 0.2. Let's put 75 just for now. We can knock off that 5 later on. And then all we have to do is solve for this small one, because it's not actually 0, it's just close to 0. And so what I like to do for this is put in another variable, because we already used x. I like using y. And it's pretty easy to solve for y using your constant. So our constant here is 5.2 times 10 to the 9th. And that's going to equal the right-hand side here, which is 0.55 moles per liter squared times the 0.275 moles per liter. And then that's going to be all over y squared, right? Y squared. So that's not too bad to solve, right? No quadratic equation needed there. You can just switch these two. So you got here 0.55 squared times 0.275, that's all moles per liter, all over the 5.2 times 10 to the 9th. And what does that come out to? So 0.55 squared times 0.275 divided by 5.2 times 10 to the 9th equals, well, teeny number, 1.6 times 10 to the negative 11, which makes y equal to the root of that. So let's see if we can't just do that here. Yeah, look at that, 4.0 times 10 to the negative 6. So a very small concentration for, this would be our concentration of CO2. And the other two we can leave as their large assumed values, right? So you got concentrations for all three now. Yay, you did it. Alrighty, so our final situation we're going to look at is if there's more than one thing on the side that's getting all used up. And so here we have, again, a very large value of the constant. And we've got 0.44 moles per liter for each of these things on the left-hand side, and we got nothing on the right. So again, we're going this way. We know that this is going to end up being large because of the size of the value of the constant, and these two are going to end up being small. However, there are coefficients here that we have to take into account, which means one of these is going to run out first. And since the carbon monoxide is being used up twice as fast as the oxygen, that makes it a limiting reagent, right? So this guy here, minus 2x and minus x and plus 2x, this is the one that's going to be pretty much 0. So really, it's only this guy that's the small one. And so we got 0.44 minus 2x approximately equals 0. We can use that to solve for the x and work out what the other two are. So we'll take our 0.44 minus 2x equals 0, and 0.44 equals 2x, and that means 0.22 is x. Great. So now we can sub that in and solve for these large values. This one is relatively large along with this value here, right? And so that means that the 0.44 minus the 0.22, and that means we end up with 0.22 moles per liter as a final amount for the oxygen. And over here, we're going to have double that, so it's going to be 0.44 moles per liter for the concentration of the carbon dioxide. And again, because this is not actually 0, just very close, we'll put in another variable. Like y, you can use whatever symbol you want. And again, it's a pretty easy solution. So keep an eye out for your limiting reagents, and you basically solve it the same way. Just figure out which one is going to be all used up or pretty much all used up, and you can make your assumptions to simplify everything. So for this one, we've got 7.5 times 10 to the 8th equals 0.44 moles per liter here squared, all over y squared times the 0.22 moles per liter. And we can reorganize that, so the y squared equals 0.44 squared all over 7.5 times 10 to the 8th times the 0.22. These are both moles per liter. So that means y squared equals, let's work it out, 0.44 squared divided by 7.5 times 10 to the 8th, and also divided by 0.22 equals, so we got 1.17 times 10 to the negative 9. And then y will be the root of that, so shift root. And I got 3 point, how many digits we got here too? 3.4 times 10 to the negative 5 moles per liter. And so that would be your concentration of carbon monoxide. And so we have the concentrations of the other two already from our assumptions, which means you're done. Yay, good job. Okay, a little recap here. I made a little graphic organizer to help you with these simplifying assumptions. First of all, when you have a large or a small value of K, you want to make sure that it's large enough by taking the constant or the concentration and dividing them and see if you have at least 100 times the value. Once you're satisfied that it's big enough to make a simplification, you're going to compare your initial concentrations to the concentrations that you would expect from the constant, right? So either you will be starting with concentrations that are almost at equilibrium, in which case the shift is going to be very small and there will be components where the change will be negligible. If the shift is very, very tiny on a large concentration, you can ignore it. You can treat it as negligible and it makes it a lot easier to solve. Now, if the initial concentrations are far from the equilibrium concentrations, that means there's going to be a big shift one direction or the other. And what you want to do is look for a component that's getting pretty much all used up. If there's only one thing on the side that's being used up, well, that's the one to look at. And if there's two of them, then you've got to decide which of them is the limiting reactant and use that one. Whatever one is getting pretty much all used up, you can assume that it's going to 0 for the purposes of figuring out the shift. And then the tiny values for both of them, you can solve with your equilibrium constant and either a variable like y or using the x that is present already in your equilibrium ice table setup. Alrighty, I hope that is helpful and gives you a strategy for solving some of those complex equilibrium problems.